Hello student, welcome back to physics class, and today we will be talking about some of the numerical problems in kinetic theory of gases. Okay, so this is the NCRT problem number 2 from the exercise of the NCRT. So here it says that the question says that I solved this question, and the question says that molar volume is the volume occupied by 1 mole of an ideal gas at standard temperature and pressure, okay, at STP, 1 atmospheric pressure and 0 degree centigrade. It is given. Show that it is 22.4 liters. That means volume we have to calculate. So this is ideal gas. Ideal gas equation we have to apply as it is written in the question also. So PV is equals to mu into R into T. That is the ideal gas equation. Okay, where P is pressure, volume, number of moles, gas constant, and temperature. So what we are having? We are having pressure in atmosphere. Okay, 1 atmosphere at STP we know. So that can be converted into Newton per meter square. Okay, and we are having the value of what? Mu also, that is number of moles. Okay, because we have to calculate for 1 mole, so mu will be equal to 1. Temperature at STP we know that it is 0 degree centigrade. Okay, so we have to convert the centigrade into 273 Kelvin for STP. Okay, and after converting these we have to put the required value in this expression to calculate the value of V, that is volume, mu into R into T upon P. Okay, so mu is 1, R we know that it is equals to 8.31. Okay, the value of R is how much? 8.31 joule per mole per Kelvin. Okay, this is the unit of that universal gas constant. And K, this is temperature upon P, that is Newton per meter square. Okay, so after solving this you will be getting something like this, that is 22.4 into 10 to the power minus 3. This is the calculation process, so I have done it here. Okay, and then you can write that for 1 liter there are how many? 10 to the power minus 3 per meter square, per meter cube, sorry. Okay, so here is the relation, that if you are getting anything something like 10 to the power minus 3 meter cube, so you can just replace it with liters, and that comes out to be 22.4 liters. Okay, that comes out to be 22.4 liters. So here is another question, that is question number 30.4. Okay, and the question says that an oxygen cylinder of volume 30 liters has initial gauge pressure of 15 atmosphere and temperature 27 degree centigrade. That means V is fixed. Okay, it is 30 liters. Okay, and pressure is T1 is how much? It is 15 atm atmosphere, and temperature is T1 is 27 degree centigrade. So after some time the oxygen is withdrawn from the cylinder, the gauge pressure drops to 11 atmosphere. Yani ki now the cylinder is still the same, it is 30 liter only, but now the pressure drops to how much after drawing it? 11 atmosphere atm, and temperature yani ki T2 is how much? 17 degree centigrade. Estimate the mass of oxygen taken out of the cylinder. Okay, so we have to find that what is the mass of the oxygen molecule. Okay, so we know that what is the relation in between the given mass into molecular weight and into number of moles. Okay, we know that number of moles, that is mu, is equal to the given mass upon molecular mass, that is capital M. Okay, this we know. So first we have to find that what is the value of this mu which has been taken out. Okay, so for that we have to put the required values of pressure also. Okay, so if the volume is 30 liters, So what will be the value in meter cube? So for 1 liter there is 10 to the power minus 3 per meter cube. Okay, 10 to the power minus 3 meter cube. Okay, so we can write that this volume is equal to 30 into 10 to the power minus 3 meter cube. Okay, this will also be equal to that value, 30 into 10 to the power minus 3 meter cube, and B will be multiplied with 11 into 10 to the power 5 Newton per meter square, and this will also be 15 into 10 to the power 5 Newton per meter square. Okay, so these are the standard units in which we have to solve our question which is there. Okay. And similarly the temperature will also be there. Okay, so if the temperature in centigrade is given to you, then we have to just what? Add 273 to convert it into Kelvin. So this will be 300 K and this will be 290. This will be 290 K. Okay, 273 plus 70, that will be equal to 290. So after knowing these values, what we have to do, we just apply the gas equation which we know. Okay, that is PV is equals to mu into R into T. So for first case, PV is equals to mu1 into R into T1, which we are knowing, and pressure is also there, different, volume is same. Okay, so we can write that mu1 is equals to T1 upon R into T1. This we can write. Okay, R into T1. Okay, into let's talk about volume also for. Okay, so P is equals to how much? P is equals to P1 is equals to how much? How much is the initial pressure? It is equals to 15 into 10 to the power 5 into volume is 30 into 10 to the power minus 3 upon R is equals to 8.31 into T. T is how much? T is equals to 300 Kelvin. Okay. So from here we will be getting that what are the number of moles that we are having initially. ठीक है, यहाँ से हम क्या पता करेंगे? What are the required number of the moles which we are having? So after solving, you will get something like 18.25. Similarly, you can calculate mu2 also by knowing these conditions. Okay, T2 and T2 and V, the value of V which is there in the second case. So I solved that question and I just write down the value directly. So it comes out to be 13.84. So now how much number of the moles has been taken out for the oxygen molecules? Okay, so that means we have to find that number of moles that has been taken out, that is equals to mu1 minus mu2, and 18.25 minus 13.84. This is what we can write. So it comes out to be 4.41. Now we are having the required number of moles. Moles taken out. We are having this, and we also know the molecular weight of the oxygen molecule. Okay, so we know that capital M is equals to 32 for oxygen. Everyone knows. Okay, for oxygen molecule. So what we do? We can calculate M also. So M will be equal to what? Mu into, that is mu2 minus mu1 minus mu2, required number of moles into M. Okay, according to the formula, number of moles is equals to given mass upon molecular weight. So this, it will come out to be how much? Whatever you are getting the value here, 4.41 into, but this, that is 32. Okay, and this will come out to be 141 in grams. Okay, this is the value of small m which we are getting. Okay, so we are getting M is equals to 141 gram. This is how we can calculate the given mass. Now let's see another important numerical which is based on RMS speed, okay, which is based on root mean square speed, okay, RMS, VRMS. So here the question says that at what temperature is the root mean square speed of an atom in an argon gas cylinder equal to the RMS speed of helium gas atom at minus 20 degrees centigrade. Atomic mass of argon is 39.9 U and of helium is 4.0 U. Okay, AMU. Okay. So at what temperature is the root mean square? That means we know that what is the formula of VRMS in terms of temperature and gas constant. It is equals to how much? Square root of 3 RT upon N. This we have derived in the previous video also that I have uploaded. That how to calculate that root mean square and what is the meaning of this root mean square and what are the outcome which we are getting. So that is another thing. But here we are talking about question number 13.9, that is the problem related to VRMS. So here for argon, let us say that the temperature that we are not knowing, okay, that the temperature we are not knowing for argon. So let us say that temperature is TA, that is for argon, and we know that the molecular weight for argon, okay, it is given that it is 39.9. And for another molecule that is helium, VRMS is here. Okay, so let this be V dash. For helium, let this be V dash. Denote it by V dash. That is VRMS, root mean square speed. Okay, so this will have the same format of that expression of VRMS. So here it is for argon, and here it will be for helium. And temperature is given. Temperature is how much? Minus 20 degrees centigrade. Okay, temperature is minus of 20 degrees centigrade for that of helium. Okay, so that means we have to put this value in Kelvin because it is the absolute temperature. Okay, so how much it will come? T of He is given. TA we have to find. Okay, so it is 3 into R into T is minus 20 degrees centigrade. So in Kelvin it will be 253 upon molecular weight is 4.0. Okay. So what we have to equate? We have to equate the root mean square speeds of both. Because it is saying that in the question that at what temperature is the root mean square speed of an atom in an argon gas cylinder equals to the root mean square speed of helium gas. Okay, that means from equation 1 and 2 we can write that square root of 3 R into TA 39.9 is equals to 3 into R into 253 upon 4. So squaring both sides, that what we can do to eliminate the square root. So we are getting something like this. So from here this will cancel out, and further if we solve 48 then we will be getting something. Okay, so it comes out to be 2572523 Kelvin here about for argon. This I have solved. Okay, so this it will come. So now let's see question number 13.7. So question number 30.7 says that estimate the average thermal energy of helium atom. First, at room temperature 27 degrees centigrade. Second, temperature on the surface of the sun. And third, the temperature of 10 million Kelvin. Okay. So average thermal energy. So average thermal energy, we know that it is denoted by how much? 3 upon 2 into K into T, where K is Boltzmann constant. Okay. So that is also known as the average energy, that is denoted by either by like this I denote, or I denoted by E bar. Okay. So that is equals to 3 upon 2 into KB into T. And we are knowing different values. We are knowing the value of K, that is 1.23 into 10 to the power minus 23. Okay, I am not talking about its unit, I am just placing the value which are here. Okay, 10 to the power minus 23 joule per Kelvin is the unit of this. The K, that is Boltzmann constant, into T. For first case, the T is given how much? It is given 27 degrees centigrade. That means 300 Kelvin. Similarly, this was E bar for first case. Similarly, for second case, the temperature is given again. That is 3 upon 2. That is for sun it is given, huh? Yes. 3.2 into 1.23 into 10 to the power minus 23 into how much it is? 6000 plus 6000 Kelvin is there. Okay. 6000 directly right. And similarly for the third, it is very easy. E bar is given 3 upon 2 into 1.23 into 10 to the power minus 23 again, and it is multiplied with 10 million Kelvin. Okay, 10 million Kelvin. So 10 to the power of 7. So whatever you will get the value in joule for energy at different temperatures. Okay, thank you.